And the main way that I want to talk about quantum spin liquids is via quantum dimer models. So there would certainly be completely different ways of presenting these ideas, but I hope you'll find that this is a reasonably concrete way, which also, I think, connects with the things that I've been saying about classical systems. So, in order to talk about quantum dimer models, I need to say something about classical dimer models, and so the first third or half of today's lecture will be about classical dimer models. And then I want a bit of a lead-in to quantum spin liquids in general, so I'll make some rather basic introductory remarks. And then I thought it would be interesting to talk about something rather old, the Lieb-Schultz-Mattis theorem, which actually now we recognize tells us something important about quantum disordered states in an important class of spin systems. And then right at the end of the lecture today, I'll get as far as defining quantum dimer models, but that will leave me with everything set up for my lecture on Thursday, when I'll talk in detail about what we know about quantum dimer models. Okay, so the first topic then is classical dimer models, and the hope is that you'll recognize what I say here as being connected in a completely obvious and natural way to the things that I told you, first of all, about the triangular lattice Ising antiferromagnet, and then yesterday about spin ice. So classical dimer models are very elementary problems, at least in their definition, in classical statistical physics. The idea is that you take a lattice and you take dimers, which are objects with a length of one bond on the lattice, and you consider, at least in the version of the problem that I'm interested in here, close packed coverings of the lattice with dimers with a kind of hardcore constraint that means that you have exactly, and to begin with, I'll talk about exactly one dimer touching each lattice site. But as I'll mention later on, we might want also to consider cases where you have a different fixed number of dimers touching each lattice site. So the basic point which I want to get across now is that if we're thinking about bipartite lattices, and I'll come on later on in this section to what changes when we go to lattices that are not bipartite. You have Coulomb phase in the senses that I discussed for spin ice yesterday, and in terms of height models for the triangular lattice antiferromagnet. So a convenient way to illustrate things is to point out that one example of a dimer model is in fact just a representation of ground states of the triangular lattice Ising antiferromagnet. And it turns out to be a dimer model, not on the triangular lattice, but instead on the dual to the triangular lattice, which is the honeycomb. Yes?
Just to be sure, what characterizes the different phases of the form of the correlation?
So in 3D, the point is that you have these so-called dipolar correlation functions. So falling off as 1 over r cubed with the specific kind of angular dependence that I was talking about. In 2D, things are a bit more delicate, as I'm going to emphasize. But one point is that the power law varies continuously with the stiffness in the height model representation. But if you use the term Coulomb phase for 2D, then you would mean that power law correlated phase.
Sorry, what's a Coulomb phase?
So the good example is the low temperature states of the ground states of nearest neighbor spin ice, as I described in the lecture yesterday, where you have these power law correlations in spins. So why call it a Coulomb phase? Well, I mean, because the effective Hamiltonian that described the entropic weight over these coarse-grained B fields that parameterize the different ground states was just like in electrostatics. I mean, in electrostatics, you have the energy density of an electric field is proportional to the field strength squared, and here we had the same kind of weight. So, if we have the triangular lattice, thinking of this Ising model, then we can construct a dual lattice by putting sites in the middles of the plaquettes and drawing bonds on the dual lattice that cross the links of the original lattice. So we can now set up a correspondence between ground states of the triangular lattice Ising model and dimer configurations on this dual honeycomb lattice, because you remember the condition to be in a ground state of the triangular lattice Ising antiferromagnet was that in each triangle we had 2 spins in one orientation and 1 spin in the reverse orientation. And in terms of bonds, that meant 2 of the 3 bonds going around the triangle are in their ground state with anti-parallel spins, and 1 bond is frustrated. So we can map between spin configurations and dimer configurations if we draw dimers on the honeycomb lattice that cross frustrated bonds on the triangular lattice. And since each triangle has 1 frustrated bond, there's 1 dimer touching each site of the honeycomb lattice. So a possible configuration might be something like that. So that's one example to illustrate the idea, but of course you can do the same kind of thing on the square lattice. and draw dimers in various configurations, just satisfying this constraint that in this particular realization we have exactly one dimer touching each lattice site.
So, which is the rule for putting these dimers? I think I missed it.
In the mapping from the triangular lattice antiferromagnet, so the point is that in the language of the Ising model, each triangle has one of its three bonds frustrated in the sense that the spins at either end are parallel, and then the rule is that we'll put a dimer crossing each frustrated bond, and that means that there's one dimer touching every side of the honeycomb lattice. Okay, so we can choose various lattices, and the next point is to discuss how the description that we had, for example, for the pyrochlor Ising antiferromagnet in terms of fluxes works for these dimer problems. So the first point is that here I'm considering lattices which are bipartite. So on the honeycomb lattice I can label sites A and B, and in such a way that the neighbors of an A site are on the B sublattice. And I can use that separation to give an orientation to the bonds in the way that I described for the diamond lattice in the case of spin ice. So in general, if I have two sublattices, I can orient the bonds, and I can introduce unit vectors in the direction that I've chosen in this way by convention on a bond I. And then I can say that the flux on a particular bond will be in this direction and of a strength which depends on whether that particular bond is occupied by a dimer or not. And I choose these strengths so that the net flux into any site of this lattice is going to be zero. So if I have Z bonds touching each site, in other words, a coordination number of Z on the lattice, then I'll have one dimer. So if I have a flux of 1 minus 1 over Z when the bond is occupied, and minus 1 over Z when the bond is empty, the net flux arriving at any site or leaving from any site will be zero. Okay. So that means that if we coarse grain, we can expect that the probability distribution on configurations will be proportional to some statistical weight, and this statistical weight we can expect will involve a stiffness, and in either 2 dimensions or 3 dimensions we can write things in terms of the flux density squared. And then following on from the things that I told you in the last two lectures, in 3D, this gives you a stable Coulomb phase and in 2D, as I mentioned, we can think of this vector potential as being the height field taken in the z direction. And in 2D, you have a Gaussian height model but in each case, you think of this as the first term in an expansion, and a few people asked me about this after the last lecture, and I mean the way to look at it is in the same sort of way that you think about constructing Landau-Ginzburg theory. The point is that you're basically doing a power series expansion for the density that appears under the integral, and you want to write down all the terms that are allowed by symmetry. So, for example, we can't have A by itself because we must have scalars and so on and so forth. And you keep all the terms which are relevant or possibly relevant in the RG sense. And in 3D, it turns out that this is the only relevant term. So if you had higher powers of B or higher gradients, those would give you irrelevant terms. In 2D, as I discussed when I was talking about the triangular lattice Ising antiferromagnet, the fact that microscopically the height field is discrete means that one of the perturbations we should think about is a cosine of the height field, and in 2D, whether that's relevant or not depends on the stiffness that appears here. So if the locking terms, as these cosines are called, are irrelevant, then we simply have this Gaussian height model, or we can be in a locked phase if the cosine terms are relevant. Maybe a minor comment to make. Here I've described things entirely in terms of fluxes, and we can use the flux idea either in 2D or 3D. When I talked about the triangular lattice Ising antiferromagnet, I talked in terms of height fields. So the point is that this dimer model we can discuss either in terms of fluxes, or we could associate heights with sites of the dual lattice, and then we'd say that we go up in height by this much when we cross a bond that's occupied by a dimer, and we go down in steps of this much when we go between sites of the dual lattice that are not occupied by dimers. Okay, any questions about that? Yeah.
Yeah. How does picture changes if I kind of put the lattice on a...
Right, okay, important question, and I'm going to come to that in just a minute, and as I'm sure you anticipating, that's to do with topological sectors in this classical language. Yeah.
So you're using this. The thing that determines the probability that it's in a entropy, and then you're saying that using this gauge field, there's a correspondence here. And then last time you gave 2 examples where you showed like high entropy has like no.
Mm-hmm.
But then is it always the case that they correspond in this way? I mean, in some general state, maybe it has a gauge field, but the B field is high, but then the entropy is whatever.
Yeah. So I could give examples like the ones that I gave last time for these dimer models, and it will work out exactly the same.
But even last time you just gave 2.
Yeah, I just gave 2 examples. So just to reiterate the obvious, the point is that microscopically, each configuration of the system is a different dimer configuration, and we want to sum over those, weighting them all equally. But unless we happen to be dealing with an exactly solvable model, that's too hard. So we'd like some coarse-grained description, and then this coarse-grained weight is telling us how many microstates correspond to each of the coarse-grained states that we're talking about. And, I mean, yes, it could all fall over, and to some extent you rely on doing Monte Carlo simulations to check that the long-distance behavior is the way it is. I mean, the most obvious way that it would fail would be if you wound up in a locked phase where the dimers would be in an ordered pattern. And even though in 3D this Coulomb phase description is stable against weak perturbations, it doesn't tell you that it's stable against some arbitrarily strong perturbation. And so you could write down some model that hadn't been studied before and start examining it and find that, in point of fact, it was in some kind of locked phase. Okay, one more thing to say here. I've described dimer models in the way they're most commonly studied, with one dimer touching each site, but you don't have to have that restriction. The important thing is that it's the same number of dimers at every site. And, for example, we can think of spin ice in terms of a dimer model with 2 dimers touching every site. So the mapping is rather straightforward. If I think of one tetrahedron of the pyrochlore lattice, the dimer model is going to live on this diamond lattice, and as we said last time, in spin ice ground states I have 2 spins pointing in and 2 spins pointing out of every tetrahedron. So I can pick some convention, which will be that I put, for example, dimers on the bonds that have the spins pointing out of tetrahedra on the A sublattice, and then I'd have 2 dimers touching every tetrahedron. So in other words, dimer models do something reasonably general. Okay, so there are 2 more points that I want to make about dimer models. The first is to do with fractionalization and deconfinement. So essentially generalizing the things that we said about monopoles in spin ice to this broader setting. So if I take out one dimer, then I have configurations with two sites uncovered, and it makes sense to think of these as sites covered by monomers. And if I just take a dimer out of a close packed configuration, then of course the two monomers are next to each other. But if I flip dimers the way I talked about flipping spins, then flipping spins in spin ice, then I can quickly wind up with a situation where the two monomers are some way apart from each other. So, for example, if I originally had a dimer here, but I remove it, then I say I've got two monomers left, and I have dimers in some configuration like that. And if I flip this dimer, then I end up with a monomer there, and I can carry on flipping and separate the monomers. So if we think about the statistical mechanics of the dimer problem, but with a couple of monomers in, then we can ask about the partition function, the number of configurations of the dimers with two monomers placed at particular sites at some separation. And in the usual way, we might think of that as the exponential of some energy. And the question will be how this energy varies with the separation of the monomers. And what I argued yesterday for spin ice was that this energy is proportional to a Coulomb law, and I say I'm using the terminology energy, but of course this is really all the physics of entropy. And then the point was that this energy goes to a constant at large separations. And we can say that the monomers are deconfined. The situation in two dimensions is a little different, and I might have talked about it when I was talking about the triangular lattice Ising model, but I ran out of time. So you remember there that we could have vortices in the height field which come about when we have excitations out of the ground state in which three spins in a triangle are all in the same orientation. And if you look in detail at the mapping to a dimer model, those vortices correspond to monomers. Well, no, actually they correspond to sources of flux because you'd have three dimers touching a site, but it's the same sort of idea. And in 2D, the energy dependence is rather different. The point is that because the height field increases, in fact, by 6 in the mapping that we had for the triangular lattice Ising antiferromagnet, as you go around the vortex, then you had the magnitude of grad h falls off like 1 over r. So if we think of the effective Hamiltonian involving the integral of the square of the gradient, then we end up with an integral in the radial direction of 1 over r squared, and with some short distance cut off a and a system size of L, this goes like log of L over A, and since that grows without bound, we say that in 2D we have confinement, but it's a rather weak form of confinement in the sense that it's only logarithmic. Any questions there?
Actually, can this confinement be observed in a simulation? Because, well, you say it's a weak form of confinement, so is it to evidence it either in an experiment or in a simulation?
Actually, in the 2D cases, you can work these things out exactly using Pfaffian techniques.
If I'm given a bunch of point-like objects that have this effective log interaction that are in, because I think KT transition is not that easy to evidence in finite systems.
Sure. Yeah. Yeah, I think you can, but I'd have to check the literature to give you a reference. But since you mentioned the KT transition, it's maybe worth emphasizing a distinction. So there are different kinds of questions that one could ask, and what's relevant depends on the physics that you're trying to investigate. So here, what I'm imagining is that we introduce a pair of dimers, a bit like the way you might test charges, and we hold them fixed, and we ask how the number of, sorry, I think I said dimers, I meant monomers. We ask how the number of configurations in the dimer background depends on the separation between the monomers. But there we're really holding them fixed, whereas if you talk about the possibility of a KT transition, which you might have wanted to do in connection with these excitations out of the ground state in the triangular latticizing antiferromagnet, then as well as thinking of the entropy penalty for introducing the vortices, you'd also want to consider the entropy gain from moving the vortices around and putting them at different locations. And of course, the idea of the BKT transition is that if the stiffness in the height field is small enough, then these vortices can become unbound. But that's introducing an extra part to the physics compared to what we're looking at over there. Yes, okay, so the next point I wanted to make is that you can imagine a much stronger kind of confinement if you have a dimer system which, for some reason, orders. Okay, so at least in 2 dimensions, these terms which are cosines in the height field can produce order if the stiffness is high enough. And actually, sticking with the triangular latticizing antiferromagnet, it turns out that by going from the case of spin a half, which I was discussing, to higher spin, you actually have a handle on the stiffness in the height model, and you can induce a transition to a locked phase. So let's think about how that would go, but all in the language of dimer models rather than Ising spins. So, ignoring any kinds of fluctuations, a locked phase might look like this. And if we want to introduce a pair of monomers into a configuration like that, then we have to have a string of dimers between the two monomers which are pushed out of this background configuration. So if I have a pair of monomers like that, then I'm forced to have a string of dimers between them, which oriented in a different way. And if I'd taken some configuration with at least local fluctuations, then this string of differently oriented dimers would affect the kind of fluctuations that are possible and give you confinement energy which is linear. Which is obviously much stronger than this log confinement. Okay, so the next point I want to make is to do with flux sectors, and then I'll come on to the difference between bipartite lattices and non-bipartite ones.
Perhaps I missed the point. Is it easy to see that it's linear now? I mean, I know it from dislocations where you have vortex chord dissociations and things like that. It's exactly the same, but this is a particular model.
I think the point is that if you've got an ordered background, then you're forced to have some identifiable line joining the two monomers, which is different from the background. And then the idea is that that line which is different will suppress local fluctuations, and the entropy penalty will be proportional to the length. But, that's it's words.
What's the transition from here to Coulomb phase? What kind of transition?
It would be a Kosterlitz-Salis transition. Okay, so if you have one of these dimer models on a bipartite lattice on a torus, then you can divide the configurations into different sectors which are labeled by the fluxes wrapping around each direction in the torus. And local reorganizations of the dimers don't change the flux sector. So, using 2D as an illustration, if I want to ask how much flux is wrapping around a torus in the vertical direction, I'll think of a horizontal slice like that, and then I remember that according to my orientation convention, if these sites are the A sublattice, the bonds are directed, say, away from the A sublattice. So the net flux will be I had a flux on a bond which was 1 minus 1 over the coordination number, which is here 4, or minus 1 over the coordination number according to whether it's occupied or empty. But the sums over these oppositely directed bonds of these minus 1 over z's will cancel, so I only need to think about occupation. So the flux will be the total number of dimers on the upward going bonds minus the total number on the downward going bonds. I might have some configuration like that, and the fact that the flux is not changed by local reorganizations means that if, for example, I focus on this loop and shuffle the dimers one step around the loop, then the contribution from this bond to the net flux will go from 1 to 0 when I shuffle the dimers around, but on the other hand, I'll pick up a contribution from this bond because it'll go from being empty to being occupied. And it's a property of bipartite lattices that whatever kind of loop you draw, moving dimers around it won't change the flux. But if we go to non-bipartite lattices, yes?
Excuse me, I will just go back a bit, because on before you erase the
Yes.
examiner lattice. I was thinking about if I move the monomer, which is in the bottom, just one side on the left, on the right, I don't see the line that will connect the two monomers. I think there's something that is more all around the.
So you want to think about what happens if I move that monomer there. To move the monomer there, well, to move this monomer, I can flip one of the dimers that's on a neighboring site. So I could flip one of these. So if I flip this one, then obviously I move the monomer to that site. If I flip this one, I move the monomer down to the bottom right. And if I flip this, I move it to the bottom left. So I'd need some more complicated reorganization to get it to here.
That was I can't see it. The only thing I got is something that will go all around a torus if this system was on a torus.
Yes. Yeah, no, I admit that I just took this example to get a picture, and I perhaps haven't explored all the possibilities. We could talk about it. Okay, so if we go to a lattice that's not bipartite, so introducing the terminology of a Z2 flux, I suppose I should say that the flux in the bipartite case is a U1 flux. Of course, microscopically, it takes integer values, but the range of integers is from a positive number to a negative number, both of order the cross-section of the system. So in the thermodynamic limit, that's essentially an unbounded range. And if the discreteness is irrelevant in the way that, for instance, the irrelevance of the cosine locking terms in the height model suggests if the stiffness is small, then the important thing is that you have an unbounded range for this flux. Whereas on a lattice that's not bipartite, you can only define a flux mod 2 that's invariant under local reorganizations. So if we think again, well, if I take, for instance, a dimer model on a triangular lattice as an example of a non-bipartite lattice, and again ask about the, well, now I no longer have a direction convention for the bonds, but I can ask about the number of dimers crossing this line. And if I think of some dimer configuration, if I take a loop on the lattice like that one and shuffle the dimers around, so with this example, if I move the dimers, I change the number of dimers crossing this horizontal line by 2. So we have a flux which is a Z2 flux, which is the number of dimers mod 2. And so on a torus, we have a Z2 number for every dimension, which labels configurations and separates them into different classes that are not connected by local dimer flips. And then the final point to make to do with classical dimer models is about what happens to monomer confinement on non-bipartite lattices. So in principle, two things can happen, but one of them is that monomers can be deconfined, with this energy or entropy going to a constant exponentially fast. And then the other question to ask about these non-bipartite lattice dimer models, of course, is to do with the correlations between dimers themselves. And those dimer-dimer correlations, instead of having the power law form that we talked about in connection with the Coulomb phase on bipartite lattices, turns out just to be short-ranged. Yes.
Was that constant exponentially fast?
Yeah, sorry, I wrote things in a way that was perhaps not the neatest way to put it. So that was what I did write. I guess what we want to think about is the energy difference, and that goes exponentially. And you can also have locked phases with confinement. Okay, so that's some background which I needed to set up partly in order to be able to talk about quantum dimer models. And I decided to cover it at this stage because it seems the natural development of the things that I was describing in the last two lectures. But now I want to switch to quantum problems, and actually to begin with to say a couple of introductory things, and then I'll come back at the end of the lecture to define quantum dimer models. Yeah.
So the general theme has been to sort of lump or group sides together to make dimers or triangles with heights. Is that a general strategy that always works, or sometimes is it better to do the opposite and maybe split the sides into many effective sides?
Yeah, so you're thinking of the AKLT state, for example, or
yeah, something like
yeah.
that.
Yeah, I think those are such different directions that it's probably hopeless to give some, general rule for when one is going to work and when another is going to work. So this is one type of approach. Mm-hmm.
Is there a way to get something like C3 flags or something between C2 and U1?
I'm not sure about dimer models, but with height models there is a certain amount of work looking at non-abelian height models and so on. I could find you some references, but I don't really know the area myself. Okay, so, I mean, firstly, just a couple of rather general points which perhaps could have gone in the first lecture if they'd fitted there. The first one is to do with the title of this lecture course. I'm talking about frustrated magnets and spin liquids, and we could think about how Néel order is destabilized by frustration. So, of course, I gave you one take on this in the first lecture when I talked about how frustration could lead to macroscopic ground state degeneracy. But we could also approach the question starting from the way that one discusses Néel order in an unfrustrated system and trying to think how things change when we have frustration. So if you think of linear spin wave theory or spin wave theory more generally, then a starting point is the Holstein-Primakov transformation. And using that, you represent spin operators in terms of bosons. So if you have a particular classical ground state, then at a given site you might choose your local z-axis for spins along the classical orientation, and then the ground state expectation of the moment will be the classical value less something to do with the fluctuations. And this quantum reduction in the ordered moment, I don't think you can write a general formula, but the way things typically look, you have an integral over a Briand zone, normalized with the Briand zone volume, and then the integrand is something like 1 over the frequency. So if you have a lot of low frequency modes, then you increase the size of the 0 point fluctuations, and in a frustrated system, that's exactly what we tend to do. So you can go on from that and ask what you're looking for. If you're looking for a quantum spin liquid ground state, so the first thing that you might ask for is a ground state with all the symmetries of the Hamiltonian unbroken, and that would be a minimum requirement. But you can think of situations which make it clear that you'd really like something more than that. And one simple one which illustrates an important point is from considering Heisenberg antiferromagnet on a square lattice, but in which you have not just one copy of the square lattice, but two layers. So imagine that we have one layer like that, and then another layer like that, and we have exchange interactions, say J, between nearest neighbor spins within each layer, and then some coupling between the sites which are located above each other, above and below each other in the different layers, which are called J primed. So if this interlayer coupling is small, then at least at zero temperature, we'll just have conventional Néel order. But if the interlayer coupling is the dominant interaction in the system, then it's pretty obvious, I think, that you'll form singlets between the sites that are above and below each other at each point in the lattice. And although that phase transition is quite interesting, the state without Néel order in the end looks like a rather simple state, because it's continuously connected to a band insulator, because you have two spins at each side forming a singlet, which is something that you could have in a tight binding model with a filled band. So, something you might want to ask for when you're looking for quantum spin liquids is an odd number of, half-odd integer spin per unit cell. So that's not to say that you couldn't have interesting spin liquid states with integer spin per unit cell, but at least there are some examples where you can see that the absence of symmetry breaking in that case is not enough to guarantee an interesting state.
Just a naive question. What do you mean by Néel order? Is that the state where we have one spin up, one spin down, one spin up, etc.?
Precisely.
Because if I remember correctly from my lessons, for a quantum system, we showed that this Néel state is not an eigenstate of the Hamiltonian.
Well, it's not an eigenstate, but if the spin is large, then the quantum fluctuations around it are small. So, for instance, in the exact ground state, we believe that the expectation of the spin would have Néel order. Well, we don't just believe it, it's been proved by the mathematicians, so we really believe it. Yes?
Is there a way to rephrase the second point? Because you rely on unit cells if you had a system without translational symmetry.
Yeah, do you have a suggestion?
No.
No, okay. No, Yeah, I'm not sure about that. Well, I mean, of course, there are lots of interesting things that happen in problems with quench disorder. But I mean, I'm thinking of infinite randomness, fixed points, and so on. But that takes us off in a different direction. Okay. So the next thing I plan to talk about is the Lieb-Schultz-Mattis theorem, which at least shows that in this case with half odd integer spin per unit cell, something special must be going on, and in particular the quantum ground state can't just be some sort of paramagnet with no structure. And in fact, we now realize, although the theorem is much older than this understanding, that if the system is quantum disordered, it must have degeneracy in the ground state for topological reasons. So what I'm going to talk about is the original version in 1D, and then I'm going to say a few hand-waving words at the end about how it extends to higher D, higher dimension. And the higher dimensional extensions were discussed with increasing levels of sophistication by Affleck and by Oshikawa and by Hastings. And the words that I'll say are at the level of Affleck's paper. So, what I want to think about is a system, and I'll talk here about a spin chain, but we could imagine a higher dimensional lattice. And the important thing is going to be that we have conserved SC. And so the example that I'll discuss things for is the XXC Heisenberg chain, where the Hamiltonian looks like this. And I'll take periodic boundary conditions in a system of length L. And what the argument will do for us is show that we can't have a ground state that's isolated from all of the other states by an energy gap. So, first of all, if that's what we're trying to show, we can assume that the ground state is unique. Because if it weren't, then that would be the result that we're trying to show anyway, and in fact, of course, in a finite system, there should be a unique ground state, even if the splitting to some symmetry-related ground state is very small. And then what we can show is that the gap to an excited state goes to zero as the system size diverges. So we can write the ground state, say, as G, and the idea is to consider a state which we construct from G and to think about its energy variationally. So we construct a state which I call psi by acting on the ground state with an operator that does slow in space rotation of spins.
John?
Yes?
Just you consider here the situation where the ground state, the unique ground state, has the same symmetries as the original Hamiltonian. Is that right? So you don't want to consider, for example, a simple ferromagnet that is...
Yeah, okay, so I want to consider a situation where the ground state is in the singlet sector. So, yeah. So that I don't have...
You don't want to just... You want to get rid of the Goldstone mode, so to say.
Well, if it were a higher dimensional antiferromagnet, I could have a ground state in the singlet sector and then I'd have Goldstone modes, but the gap to the lowest lying Goldstone mode in a system of finite size would be finite, and it would go to zero as the system size went to infinity. So, I mean, I agree that it's crucial that I have a ground state in with no degeneracy following just from spin rotations. So this operator that does spin rotations, well, of course, I generate spin rotations with SZ, so it's an exponential of SZ operators at the different sites, and if I had the same coefficient for the rotation operators at each site, then this would just be some thing that was a global symmetry of the Hamiltonian, but the idea is to have the coefficients vary with position, but in a way that's slow if the size of the system is large. And then we need to show two things. So the first one, which is important, which I'll actually come to second, is that the state that we generate by this slow rotation is orthogonal to the ground state. And then secondly, we want to use this state in a variational estimate. So we want to compare the expectation of the Hamiltonian in this state with the ground state energy, the eigenvalue for this state G. And that's the same thing as taking the ground state expectation of the Hamiltonian rotated with this operator compared to the unrotated Hamiltonian. And to look at that expectation value of the energy, and what we want to show is that this is small in some sense. So, if we remember what happens when we rotate a single spin, yeah.
How do you make the equality at the end of the last equality?
Okay, so thinking about the first term. Okay, so once we've, what I have here in the first instance is U dagger E0 U. But E0 is just a number, so I can combine U and U dagger and replace it with 1. And then I'm just left with E0. But H acting on G gives me E0. That's actually my definition of E0. Okay, so if we think of the effect of rotations in the Hamiltonian, we had spin raising and lowering operators. So the effect of a rotation through an angle theta is to multiply, for instance, the spin raising operator by e to the I theta. So if we look at what happens when we rotate the terms that describe the xy parts of the exchange, then we get a factor of e to the 2 pi I, and the differences in rotation angles at these two sites are just 2 pi I over L, so we get a factor of 2 pi I over L times S plus S minus. So, when we put things together, we have that psi H minus E0 psi is, from these hopping terms, we get, from this phase, we get 2 pi over L. So this is all from the H part of this expectation, and then from E0, we get minus 1, and that multiplies the expectation of Sn plus 1 minus. And in the Hamiltonian, there was a sum over sites, so there's still that sum over sites. And then we also had some SZ terms, but those are left invariant under these rotations, so their contributions from these two terms cancel each other. So then the basic point is that if L is large, we can think about expanding the cosine, and this will give us something that's of order 1 over L squared. And on the other hand, we've got a sum over sites, so that gives us a factor of L, but taking the two things together, this goes to 0 as L goes to infinity. The other thing we need to check is this claim that the state we've generated is orthogonal to the ground state. I think in view of time, I'll leave that as an exercise, but I'll just give you one clue as to what you need to do in order to get started. So first of all, you want to think about translations. So T will be an operator that's a translation by one lattice site. And since the ground state is unique, you have that T on G should just be G. And then simply from the definition, you can think about what the effect is of translations on this rotation operator that generates our trial excited state, and you can show that the translation operator acting on this rotation gives us minus the rotation. And this is a crucial point if S is, the spin here is half odd integer. And then if you put these two things together, you can show that T acting on psi gives us minus psi, so it has to be orthogonal to the ground state. Okay, so just to close, we need to look at this result and think what we've learned. So there are different possibilities according to what's going on in the system. Yes?
Which are the underlying assumptions for the Hamiltonian? Has to be local or?
So it should be local, and we need SC to be conserved. That's it. So we know that there's at least one excited state with a gap that closes as the system size diverges, and there are two familiar ways to get that. So one is if we have some global broken symmetry with a local order parameter. So I was thinking of a discrete broken symmetry. So in this XXC chain, I hope when I wrote down the Hamiltonian, I had a separate parameter in front of the SC-SC coupling. And so if I make that large compared to the transverse coupling, then I get, in the ground state, Ising ordering. So that would be gapped, but I'd have two low-lying states corresponding to symmetric or antisymmetric combinations of spins up and spins down. Or I could have gapless excitations and if the anisotropy if I'm at the isotropic point, or close to an XY chain, then I have gapless spin-on excitations. But if I have a gap system with no local order parameter, then what this says is that there must be at least two two ground states which will correspond to different topological sectors in a topologically ordered system. there are no gapless excitations and no long-range order, then there must be topological degeneracy. And in the quantum dimer models, which I'll talk about in the next lecture, you can track that back to the degeneracy in terms of sectors that I discussed for classical dimer models on non-bipartite lattices.
Could you explain again what's the second familiar way to have gapless excitation? Because the idea is that if you have gapless excitation, you need to have gapless excitation. That's why the two words, right?
Yeah, so what I'm trying to say is that there are physically, I think here, all right. Yes, okay, I see that the way I've written it on the board doesn't look very illuminating.
The first is a degenerate set of ground states, and the second is a continuum of excitations down to zero.
Yeah, exactly. So this argument just says that there's at least one excited state that in the thermodynamic limit is degenerate with the ground state, and it could either be that that excited state belongs to some branch of gapless excitations, or it could be it's one of a discrete set to do with broken symmetry, which can be described by a local order parameter. But then the third possibility, which is what we're interested in here, is a situation in which there's no branch of gapless excitations, there's no local order parameter characterizing a broken symmetry. Instead, there's topological degeneracy. Okay, and the theorem extends to higher dimensions, and one simple way of thinking about it is to imagine a system on a strip, and then the width of the strip needs to be odd in order that you have half-odd integer spin, and the effect of having a strip is that whereas the estimate previously was that the gap was bounded by 1 over L. Now, if you have strip width M, the gap is bounded by M divided by L, and so you have to take the thermodynamic limit in a particular order, or otherwise take a more sophisticated approach. Okay, sorry for overrunning.